Have you ever wondered if light can be trapped? It sounds like something straight out of a sci-fi movie, right? But what if I told you it's not only possible, but it's happening all around us, and even inside our bodies? Today, we're diving deep into the fascinating physics of how light gets caught. First, let's get one thing straight. In the vast emptiness of space, light travels in a perfectly straight line at an incredible speed, about 300,000 kilometers per second. Nothing can stop it unless it hits something. But when light moves from one medium to another, say from air into water, something interesting happens. It bends. This phenomenon is called refraction. You've seen this yourself. Ever noticed how a straw in a glass of water looks bent at the surface? That's refraction in action. The light from the straw bends as it passes from the water back into the air before reaching your eyes. The amount light bends depends on the refractive index of the material. Think of it as a measure of how much a material can slow down and bend light. Air has a low refractive index, while water and glass have higher ones. The bigger the difference in refractive indices between two materials, the more the light bends. Now here's where it gets really cool. If you shine a light from a denser medium, like water, into a less dense medium, like air, at a shallow enough angle, the light will bend away from the normal line. As you increase this angle, you'll eventually hit a special point called the critical angle. At this exact angle, the light doesn't escape into the air. Instead, it skims right along the surface, perfectly parallel to the boundary between the water and the air. So, what happens if you go beyond this critical angle? This is the magic moment. The light can no longer escape. It doesn't refract into the air at all. Instead, it gets completely reflected back into the water, as if it hit a perfect mirror. This is called total internal reflection, or TIR for short. The light is effectively trapped. This isn't just a neat party trick. It's the fundamental principle behind fiber optic cables. These cables are incredibly thin strands of glass or plastic. Light signals, carrying massive amounts of data for our internet, phone calls, and TV shows, are beamed into one end. They travel down the fiber, constantly bouncing off the inner walls at an angle greater than the critical angle. Because of total internal reflection, the light signal stays trapped inside the fiber, zipping along for thousands of kilometers with almost no loss of signal. It's like a light pipe, guiding the information exactly where it needs to go. Nature also has its own version of this. The mesmerizing sparkle of a well-cut diamond is a perfect example. A diamond has an incredibly high refractive index, which means its critical angle is very small. When light enters a diamond, it bounces around inside multiple times, undergoing total internal reflection before it finally escapes through the top facets. This traps the light temporarily, causing that brilliant fire and sparkle we all love. Even more amazingly, scientists are pushing the boundaries even further. In labs, they've created photonic crystals, which are like microscopic obstacle courses for light. These structures can be engineered to trap specific colors of light, essentially holding photons in place. They've also used supercooled clouds of atoms to slow light down to a crawl, and in some cases, stop it completely for a short period before releasing it. It's like putting light in a temporary jail. From the internet cables that connect our world to the dazzling beauty of a gemstone and the cutting-edge science in laboratories, the ability to trap light is a powerful and essential phenomenon. It's a beautiful dance between light and matter, all governed by a simple rule. Once you pass the critical angle, there's no escape. So the next time you browse the web or admire a sparkling diamond, remember the incredible physics at play. You're witnessing light being cleverly and beautifully trapped. Thanks for watching, and if you enjoyed this journey into the world of light, don't forget to like, share, and subscribe for more science adventures. See you in the next one.